Have you ever wondered why copper wires are good conductors but sulfur doesn't conduct electricity? This difference lies in how atoms deal with electrons, and that's exactly what metallic and non-metallic character explains. So let's start from the root. Metallic character refers to the tendency of an atom to lose electrons and form positive ions. For example, when a metal like sodium is supplied with energy, it loses one electron and becomes a cation. Sodium atom gives sodium ion plus one electron. On the other hand, nonmetallic character is the tendency of an atom to gain electrons and form negative ions. Take chlorine, it readily gains an electron to become chloride. This is written as chlorine atom plus one electron gives chloride ion. In summary, metals lose electrons and form positive ions, while nonmetals gain electrons and form negative ions. Now let's dig into the factors that influence whether an atom behaves like a metal or a nonmetal. First up is atomic radius. When atomic size increases, electrons are farther from the nucleus and held less tightly, making it easier to lose electrons and increasing metallic character. Conversely, smaller atoms hold electrons more tightly and more easily gain them, which boosts nonmetallic character. Then comes ionization potential, that is, the energy required to remove an electron. A low ionization potential means it's easier to remove an electron, increasing metallic nature. High ionization potential, on the other hand, favors nonmetals that attract electrons. Think of sodium, a large atom with low ionization energy. It behaves as a typical metal. Now contrast that with fluorine, a small atom with high ionization energy, an extremely reactive nonmetal. So remember, large atoms with low ionization energy tend to be metals, while small atoms with high ionization energy tend to be nonmetals. As we move across a period from left to right, the atomic size decreases and the ionization potential increases. This makes it harder to lose electrons, so metallic character decreases. Meanwhile, nonmetallic character increases as atoms become better at attracting electrons. Let's look at period 3. Sodium, magnesium, and aluminum are metals. Silicon is a metalloid. Phosphorus, sulfur, and chlorine are nonmetals. Argon, at the end, is a noble gas. This trend happens because electrons are added to the same shell while nuclear charge increases, pulling the electrons closer and reducing the size. The result? Across a period, metallic character decreases, non-metallic character increases. Let's now move down a group. As we go down, atomic radius increases because new shells are added. This means outer electrons are farther from the nucleus and less tightly held. As a result, metallic character increases. It becomes easier for atoms to lose electrons. Simultaneously, nonmetallic character decreases because the larger atoms are poorer at attracting electrons. Take group 14, at the top is carbon, a typical nonmetal. Go down to silicon and germanium, and you hit metalloids. By the time you reach lead, you're looking at a full metal. So down a group, atomic radius increases, ionization potential decreases, metallic character increases, nonmetallic character decreases. Metals are good reducing agents. They love to donate electrons in redox reactions. Nonmetals, on the other hand, are strong oxidizing agents, eagerly accepting electrons during reactions. In industry, highly electropositive metals like sodium are vital for extracting metals and generating electricity in batteries. In the lab, a simple example is the reaction of dilute hydrochloric acid with zinc. Zinc plus hydrochloric acid produces zinc chloride and hydrogen gas. Remember, the easier it is for an atom to lose or gain electrons, the more reactive it becomes in chemical processes. Let's wrap it up. As you move across a period from left to right, atoms shrink in size, ionization potential shoots up, metallic nature fades, and nonmetallic nature shines brighter. Move down a group, and the opposite happens: atoms grow larger, ionization potential drops, metals get stronger, and nonmetals lose their edge. Position is key. The left bottom corner of the periodic table is the metallic stronghold, while the top right corner is the nonmetallic kingdom. And remember, these metallic and nonmetallic traits shape bond types, reactivity, oxidation states, and the very compounds that make up our world. I hope this session helped you connect the periodic table to the actual behavior of elements in labs, industries, and even nature. In the next class, we'll move on to more fascinating properties that shape the periodic table's elegance. See you there.